filter came from out of that signal. Okay? So the highest value is exactly when these things match. There are a couple of reasons to explain that. Here's the one that I like best. Pretend for a moment that both of our signals were normalized about, so they were sort of shifted so that they were about zero. So sometimes they went positive and sometimes they went negative. Okay? And remember, we've got the scale being approximately the same because they scale up so the standard deviation is 1. If I take one filter and I lay it over the image and I'm going to multiply them and then sum them up, remember, some of my values are positive and some of them might be negative. I realize this is the first time we've talked about negative signals. In fact, on the drawing here, you'll notice it's 0 in the middle. But if I've got positive numbers and negative numbers, and I've got positive numbers and negative numbers in my filter, if I want to do a multiplication and have it come up as high as possible, when does that happen? Well, the obvious intuition is, well, whenever my pixels in the image are positive, I want my coefficients in my filter to be positive. Because positive times positive is what, Megan?
Positive times positive?
Yeah, positive. And what do I want where the image is negative? I want the filter coefficients to be negative also, right? Because negative times negative is what, Megan? Positive, very good. You know, she went to film school, but she's doing great. Anyway, and so if you think of sort of a filter as having, because we've scaled it, you know, it can't go arbitrarily high and arbitrarily low. If you get that signal to be lined up exactly, so wherever it's positive, the other one's positive, and where one is negative, the other is negative, you get the maximum value. There are a lot more sophisticated ways of showing this involving differences in distributions and things like that. They all basically will show you that the maximum value you can get, the product of these, is when they're exactly the same. We can do the same thing in 2 dimensions also. So here is a different pepper image, right? And this is a little chunk of the pepper image, happens to have some garlic in it too, all right, taken right sort of from here. I could do normalized correlation of this small patch on the whole image, and I can plot that, and when you do, you get this answer, all right? And you see this little spike here? That's what happens when the filter lands right on the spot in the image that it was taken from. You get this, again, the positives line up with the positives, the negatives line up with the negatives.
Okay, let's write some code. We'll use one-dimensional data to begin with. Given a discrete signal S as a vector and a template T, our job is to find where that template occurs in the signal. This is just like finding a substring in a longer string. Here we are playing with numerical values, which has some implications. Note that here we want to find the starting index where the template occurs. Let's print out the signal and template to see what we mean. Here we've used colon to generate the sequence of column numbers. Size of S, 2 is the number of columns in S. Let's see what the output looks like. The top row here is the column numbers. Can you find the template? Yes, it is located here, starting at index 5 in the signal. So this is what I want you to do. I want you to write a function, findTemplate1D, that takes 2 parameters t and s, the template and signal. It should return the index where template is found in S. Once the index is found, we should be able to display it. Let me get you started with some template code. By the way, you most likely need to use the image package. Make sure you test out your function with different signal and template values. When you submit your code, your function will be evaluated against other test sets. As you might have guessed, we want to use normalized cross-correlation. This correlates the template T over the signal S and returns a normalized set of values. You can find out the maximum value in this result set using the max function. This corresponds to the best match location. When given 2 output arguments, max can actually return the index of the max value as well. Isn't that what we wanted? Let's look at the result. So we see that the returned index is 7, but the correct answer should be 5. What happened? The correlation function actually starts comparing from the first point of overlap between the template and the signal. Here the template has 3 elements. So comparison starts where the third element overlaps with the first element of the signal. and the window moves from that point forward till the end and beyond. The operation stops at the last point of overlap. Let's look at the values of C to figure out if this is really the case. We use the same trick here to display column numbers. And let's comment out other output code for clarity. As we can see here, we have 16 values. Our signal had 14. The first two coefficients are from positions where the template was partially outside the signal. Therefore, index 3, which is the length of the template, corresponds to the first position in the signal. We have to account for this offset when returning the index value. One way to think about this is that the index value returned by max is the raw index. In order to get the correct index, we need to subtract the size of the template and add 1. Let us restore our original output lines and look at the output. Now we have the correct index, 5. This is the starting position of the template found in the signal. Let's try a different template. Alright, as expected, the template is found at position 7. Note that we are not constrained by templates that have exact matches. For instance, we can try a template that only partially occurs in the signal. Quite impressive. The template is found in the correct position, even though there is a mismatch. A partial mismatch would result in a correlation coefficient that is less than 1, but it might still be the maximum across all other elements.
Let's continue exploring this idea of using filters as templates of what we want to find in 2 dimensions. Okay? So a template is a thing that you give me and you say, I want you to find something else that looks like this, and we're going to do that through filtering. And here's a nice example, courtesy of Kristen Grauman as well, I believe, although I'm not sure she made, that's one of the, by the way, this is early in the class. You're going to see a lot of slides that have somebody's name next to them, because I've got them. And then what I later discovered is many of these slides came from other people and from other people. So the name that I put down is the name that I was able to track it towards, and the rest of us on the internet were just making our way. All right. So here's a very simple example. So here we have a scene on the left, and we've got this template on the right. All right. So this is the thing that we want to find. And you look over here and you say, oh, I see where it is. It's right over here. So what we would like is our system to spit out something like this. Say, aha, here's my little green box. Well, what we can do is we can actually do this through a normalized correlation. If I take that mask kernel template on the right and I do a normalized correlation with the image on the left, what I get is a map or a correlation image that looks like this. Okay? And you'll notice that where black lies over black and white lies over white, you can think of that as positive or negative. So I get some brightness over here and some brightness over here, but my really bright spot is right there, because that's the template having landed in the right place. So that's how you're using correlation in order to do this detection, because now we're thinking of filters not so much as doing an averaging or a blurring, but as actually being a template that we're looking for.
I bet you're itching to do this yourself. Here's the function I want you to define. Find template 2D. It takes a template and an image as input and returns the x and y coordinates where the template is found in the image. I have just the image to test this out. I'll cut out a glyph from this tablet, which will serve as our template. Remember, you want to find where the top left corner of the template occurs in the image. Also note the order of the returned coordinates, y, x. As before, we use normalized cross-correlation. Since the image is a two-dimensional matrix, we need to be careful when finding the maximum. Simply writing max of C would compute the column-wise maximums. Indexing C with a single colon flattens it. Therefore, max of C colon would compute the image-wide maximum. We use a slightly different trick to find the location where this maximum occurs. The find function directly returns the row and column, that is the y and x coordinate of the desired location. Remember that these are raw indices into the matrix of correlation coefficients. We need to account for the offset by subtracting the size of the template along the appropriate dimension and adding 1. And that's it. Let's see what y and x values we get back. Alright, 75, 150. Isn't that where we cropped out the glyph from? Indeed, those were the top and left coordinates. We can do some additional plotting to make the result more intuitive. Here we first show the original image, and then we plot a red plus on top of it where the template was found. Since this is not a fully interactive environment, we have limited plotting capability. In a local installation of MATLAB or Octave, you can do a lot more, like draw a rectangle where the template is found.
So those of you that are old enough will remember, and especially if you're from the United States, you remember that for a while there was this whole bunch of books out there called Where's Waldo? And they would give you a scene that looked like this on the left, and your goal was to find, here's Waldo right here, kind of blurred up, hard to see. That would be my template maybe, and I want to find Waldo. And if you take a look at this, can everybody see where Waldo is? Well, he's right there, okay? And we go back there, okay? You can see him. Okay, there he is, all right? So the question is, how could you do this doing the template matching? Well, we would do the same thing before. We take our image, we take our little template, and maybe you can see over here on this correlation map, all right, there's that bright spot right there. And you'll notice that everywhere else it's hardly bright at all, but right there, that's that bright spot.
Besides looking for Waldo, what is template matching good for? Let's look at some cases. Can you find lines in an image with templates, including vertical, horizontal, and diagonal lines? How about faces? Some small and some large. Icons on a computer screen. Can we use template matching to find cracks and fissures in metal components? This is actually something that computer vision is successfully used for in real assembly lines. Mark the situations in which you think template matching can be fairly successful. Since lines in an image can be of different lengths and orientations, you cannot come up with a single template to find them. Although you can use a bunch of templates at different orientations to find parts of lines, there are much better options for this purpose. Template matching is in general not suitable for finding arbitrary lines. The case for finding faces is arguable. Again, due to the possible size differences, you cannot come up with a single template. Moreover, faces can be front-facing or side-facing or rotated at any arbitrary angle. Either answer is correct, although, as we'll see, there are much better ways for doing this as well. Finding and recognizing icons on a computer screen is a fairly predictable task. This is because icons are usually shown upright, and their size is from a limited set. Therefore, template matching is suitable in this case. Cracks and fissures hardly have a predictable shape. Therefore, they cannot be detected by template matching. Are there any other good uses you can think of, or cases where you're sure that template matching is bound to fail? Share with your peers on the forum.
And in fact, that's shown here. So it says, what if the template in the scene is not identical to some subimage? So here we have a scene and we have a template. Well, it turns out that the best location of this template in this scene is right there. It actually finds the same car. Now you have to worry about scale and orientation and all that stuff we're going to talk about later in the class. But even though the cars are quite different, the fact of the matter is it has sort of bright stuff here and dark round things there. This has bright stuff there and dark round things there. So as a template, it's not awful. So that's using these filters as templates. Here's a question for you. Would this method actually work for finding Waldo in most pictures? A, yes, normalized correlation is a powerful thing. B, no, we don't actually have the right template. C, partially. Explain how. Whenever I ask you that, the answer is always partially explain how. And here's why. Yes, normalized correlation is powerful if you happen to have the template. And in here for Waldo, we had the exact template. How do I know? I actually cut it out of this picture to begin with, and I made a template out of it. But if I don't know what Waldo's going to look like, all right, so he's got that same dumb hat and the striped shirt, but he could be bent over, etc., whatever. I don't have the exact right template. But now think about stepping back and blurring it just a little. So there's kind of red stuff up here and reddish, whitish, pinkish stuff down below. So your template is sort of close. So you might actually be able to get some candidate examples. And actually that ends this lesson. Essentially, we're using filters to localize interesting areas in the image that have some sort of property that makes the filter respond well. So what we're going to do going forward is we'll use some special filters to compute some